Hello everyone, welcome back to another session by K21 Academy. Today our experts trainer will be discussing about SQL dedicated pool architecture. So let's get into the video.
The architecture of the dedicated SQL pool. Now, dedicated SQL pool is a PDW, parallel data warehouse, right? So understanding its architecture is super important for understanding all those things like distribution types, and then you have partition strategies, and then you have all those things that you typically will see in your laboratory that they will talk about, right? Indexes, right? Statistics, CTAS statement, right? So architecture is super important. It is also important for your interviews, right? So when you go to interviews, you will find questions on the architecture of the SQL pool, dedicated SQL pool, right? So let's now see how is it built, right? So first of all, there is a master node inside it, right? That master node is called as your compute node, oh sorry, control node, right? So you have a master node that is called as the control node. So control node, you have the control node. The control node is an interface to us, right? We interact with the control node, right? So our query, the query queue, is submitted to the control node. Control node parses the query, prepares the parse tree, looks at the relational algebra of the query, the domain algebra of the query, get an algebraized tree, and then prepare the query plan and optimize the plan and get a plan, read the data. So it does a lot of things internally. We are not concerned by looking into its mechanics, that internally what it does, right? So basically it is a driver of the query, right? It manages the context of the query. What is your query all about? What tables it is touching? How to read the data of those tables? And basically the query will be processed in parallel. So it has to chunk the data, right? It has to create chunks of the data and send that chunks to multiple processors to run your query in parallel. So control node manages the context of the query, interacts with the processors, which are now going to come. The control node, apart from it, we have what are called as distributions, right? What are called as distribution slots, right? So apart from these, you have something called as distribution slots. Distribution slots. And how many of them? Distribution slots? Total 60 always. Always total 60. So there will be total 60 distribution slots, right? I will draw them as buckets because then we will be able to reason about them in a proper way, right? So there will be buckets and there will be total 60 buckets. Okay. So let's say this is 1, 2, 3, and here is the bucket number 60. So total 60 buckets, which are called as distribution slots. Okay. So what does happen? Why distribution slots? We're going to come to it a little later. Apart from the control node, the distribution slots, it also has something called as a pool. Now comes the concept of a pool. It has a pool of SQL engines, pool of Azure SQL DB relational engine. Yes, Azure SQL DB relational engine, query relational engine, which we call as compute pool, right? Compute pool. So it has a compute pool of Azure SQL DB relational engine. So here you have a pool. Pool means a cluster. So here you have. So this is SQL DB relational engine. I will simply write RE, relational engine, right? So here you have the relational engines, and so on and so forth. You're going to have many of them right? Maximum you can have 60. Okay, maximum you can have 60. So number 1 to 60, you can have 1 to 60. Okay, minimum 1, maximum 60. And this number is configured by us by configuring something called as DWU, data warehousing units. So the amount of DWU that you purchase from Microsoft will decide how many of these engines you will have in your cluster, how much RAM they will carry, how much log writing space they will have, and so on and so forth, right? There is a very beautiful chart that summarizes all that, for how much DWU we give how much resources to you. All this that you see, right? All of this, that is control node, distribution slots, and the pool of SQL DB relational engines, all of them are connected via a bus, right? A data movement bridge bus. So all this is connected via the bus. Okay, so all this is connected via the bus like this, right? All of this is connected via the bus. This bus is called as the data movement service bridge, right? DMS bridge, data movement service bridge, DMS bridge. This is called as the DMS bridge. And they all are connected to it. Slots and everything is connected via it. So what is the reason? Control node can send commands to them, can send data to them, and so on and so forth, right? Commands and all that. So control node can talk with these people, right? And they can also talk with each other, right? Exchange and shuffles. So they can also do shuffling of the data between each other via this bridge, and they can exchange the data and shuffling, all that. Okay, so they can do inter-node communications, inter-compute node communication, inter-compute node communication, and that we have to minimize. Yes, shuffling and exchanges have to be minimized, because if you do a lot of shuffling of the data between these processors, because they are essentially doing the query computation, your query performance will regress if there is a too much of network IO. So if they are very chatty, if they're talking to each other too much, they are moving the data too much, the query performance will decrease, right? They should not be chatty. They must have their own data to process and give back the results to the control node. Okay, so intercompute node communication has to be minimized. Otherwise, it will lead to the regression of the query performance, suboptimal query execution. All right, so this is the components. First of all, a control node, a distribution slot, a pool of SQL DB relational engine, and which is called as a compute pool. Distribution slots always 60, this 1 to 60, and then the data movement service bridge. Control node can talk, whereas they can also talk with each other, but we're going to have to minimize the exchanges and the shuffles, otherwise the performance of the query will regress. The data of your tables is stored in the backend into the Azure Storage, right? As your MDF and LDF files, as you all know. So this is Azure Storage. And your tables, whatever the tables are, let's say table T1, table T2, their MDF and LDF files are sitting here. Right? Multiple tables, their data is eventually persisted over here, right? Backend. So what happens when you do a query? what happens when we do a query. So we say a query, and the query, let us say, join the table T1, join with the table T2 on T1 dot customer ID is equals to T2 dot customer ID, right? So T1 dot customer ID is equals to T2 dot customer ID. So let us say they have a common column called as a customer ID, and we join. MDF files are data files, LDF files are log files in the structured SQL warehouses. Okay. So T1 join T2, T1 dot customer ID is equals to T2 dot customer ID. So that's the query that you're asking. Control node gets the query, does the parsing of the query, prepares the parse tree, then checks the relational algebra, domain algebra, gets the algebraized tree, then send it to the optimizer. The optimizer prepares a plan, right? And then eventually it starts executing the plan. Okay. So what you need to now do is this control node issues a command to the Azure Storage to send the data of T1 and T2. Right? You are asking table T1 and T2. So control node gonna send a command, right? It will communicate to the Azure Storage Engine, a command C, telling that I want table T1 and I want table T2 to do the query that I have at my hand. And that data of table T1 and the table T2 will be moved into these slots from the Azure Storage Engine. Okay. So table T1 and table T2 data that you're asking, control node going to issue a command. The data goes here. Here is also a internal DMS bridge that Microsoft has, right? Azure Storage on the service endpoints. So T1 data of table T1 and T2 are filled in these buckets. So the table T1 and T2 data will be broken down into 60 buckets. So some rows will land up here, some rows will land up here, some rows will land up here, and so on and so forth. So the data is now divided into 60 total buckets. Okay, table T1, some rows here, some rows here, some rows here, and 60. Table T2, some rows here, some rows here. And these buckets are serverless. It's not that these buckets have a limit. They will fill. They will divide the data into 60 equal parts. Okay, table T1 and table T2 will be divided into 60 equal parts and filled here. And then what's going to happen? Depending on the number of engines you have here, the buckets will be distributed in that number. Rows are distributed. Some rows are here, as I'm telling you. Rows are here, some rows here, some rows here, some rows here, and so on and so forth. Rows, right? You're going to fill up the rows here. And now what? These buckets are then distributed here. Okay, so depending on the number of engines you have. So let us say you have, how many buckets you have? You have total 60 buckets always. And how many engines you have? Compute engines, right? Compute nodes, you can say compute nodes. Let's say only one compute node you have, one. So how many buckets will be given to this one? All the 60. Let's say you have two over here, this one and this one. How many will be given to each? 30 will be given to each. Bucket 60 by 2, 30. Let's say you have 3. Then how many? 60 by 3, 20 buckets given to each one of them. Let's say you have 4. 60 by 4, 15 buckets. Let's say you have 5. 60 by 5, that is 12. 12 buckets to each guy. And so on and so forth. If you have total 60 engines, which you can have at maximum, 60 engines, 60 buckets you have total, each one will be given 1. So you can clearly observe that if you do more parallel work, the data that your engine has to process is very less, only one bucket, right? Correct. Do we need to define the slots and engines, or they automatically spin up until 60? No, that depends on DWU. Okay, DWU, we're going to come to that. This is not serverless. This is not serverless. You configure how many DWUs and you get them. Okay, you get the number of DWUs. DWUs, on the basis of that, there is a chart. There is a chart that tells us that if you have purchased these many DWUs, you get these many engines. Okay, so like this. Correct. So you can clearly observe that if the number of engines are more, that is the horsepower of your pool is more, they have to just process small data. So parallel work will happen and your query will run fastest. They are just processing a single bucket, right? Let us say you have a project manager, the guy gives you all the work. You're going to take a lot of time because all the work is given to you. Let's say you have a colleague, half work you're doing. Let's say you have total 60 members in a team and there are 60 assignments to be done. Each one of you do one assignments, let's say 45 minutes maximum required. Within 45 minutes, all the work is done. That's what it is, right? Parallel distributed work. So this is the format. They process, the buckets are given to them. They execute the query on the data of the bucket, send back the output to the control node. Control node collates the output and send back the results to you, right? So result comes here. We get the result here. So they're gonna process, give back. But during processing, they may ask control node, hey control node, I am doing something for which I need a bucket given to this guy, or some of the rows given in the bucket to this guy. So this bucket was given to this, and this bucket, let's say, was given to this guy. This guy says, hey, I need some data from that bucket 3, which you have given here. So it will ask a shuffling and an exchange, which will increase the internode communication, and that can basically regress the performance because network IO will increase. This will become a lot of chatty. So to control the internode communication, this component, the game happens here, right? The game happens here. And what is that game? Right? Game happens here. And what is that game that happens here? How are you filling the buckets? Fill the buckets in such a way that they don't ask each other. That's what you can do. Control node will try to minimize that they should not ask for shuffling. So the control node will intelligently ask the DMS bridge to fill the buckets here. And those are called as distribution property of the tables. Distribution property of the table. So what is the distribution properties of the table? Distribution property of the table. Distribution property of table. Every table in the warehouse, whatever the table you may have in your warehouse, they have something called as a distribution property that tells the control node how the data, that is the rows in that table, has to be filled in these buckets. Every table has a distribution property. That property tells the control node that how these buckets have to be filled, what strategy has to be adopted to fill them. So there are 3 kinds of distribution properties. Okay, what are they? You have 3 distribution properties. One is called as round_robin. Round robin. Second is called as replicated or broadcasted. Replicated/broadcasted. And then the third one is hash. These are the three distribution properties that you have. Okay. So now the question arises, what are they? And this is one of the most important point to remember. These distribution properties are super important, very crucial and very important topic at our disposal. Okay. So three of them: round robin, broadcasted or replicated, and hash. What is round robin? Round robin is simple. I hope you might have played the game of cards, right? So how do we distribute the cards, the pack of card, in a round robin fashion? So let's say this is the player 1, this is the player 2, this is the player 3, and this is the deck of 52 cards. Okay, so this is the deck of 52 cards. So how will we distribute? Generally we distribute in this way: card 1 here, card 2, card 3. So card 1, card 2, card 3, card 4, card 5, card 6, card 7, card 8, card 9, and so on and so forth until you come to the last set of cards, the 53rd card here, the 52nd card here. Total how many we have? 13 times 4, that is 52 cards, right? So 49th card here, 51st card here, and the 52nd card here. That's how we distribute cards, right? Round robin fashion. So you have tables, table T1 and table T2. Let's say table T1 has 350k records in it, rows in it. And let's say table T2 has, let's say, 170k records in it. So how will it fill the buckets? Total 60 people are waiting, right? Total 60 buckets are there. So interpret each row as a card. First row goes to first bucket, second row goes to second bucket, third row goes to third bucket, and so on and so forth. It's gonna fill it in a round robin fashion. First row here, second row here, third row, fourth row, 60th row, 61 row, 62nd row, 63rd row, 120th row, 121st, 122nd, 123rd, 180th row. So it will round robin the rows of both the tables, if both the tables are round robin. Round robin. Simple. Rows are being distributed as if you're giving a deck of cards to the 60 people. What is the purpose of round robin? Round robin is not a query table, right? We're going to discuss it very shortly. I will demonstrate a lot of things today. It's not a query table. You don't do your reporting ad hoc, whatever. You do not do queries on it. It is not a part of dimensional modeling. You don't do reporting on it, dashboarding on it, ad hoc on it, interactive queries on it. No. Then what is it for? It is for loading the data from external sources into the warehouse. It is the port of warehouse. The warehouse gets the data from external places into this round robin. It has the best performance of loading. Round robin generally has, not always, generally, right? 99% of the time, best loading performance from external sources. Best loading performance from external sources, right? So it's basically a port of a warehouse. Warehouse gets the data from external sources into a RR table. It's not for queries, it's to load. Let's load the massive volumes. Yes, staging. You are absolutely right. The correct word is staging, loading from external sources. Best loading performance from external sources, RR table, not a query table. Now you can deduce some things out of this. It's not a query table. So if it is not for select operations, heavy select operations, your typical reporting and all that, so then it means that there is no need for an index on this table. So no index should be used, but that's called as a heap, right? No index, heap. But you will find engineers, warehouse engineers, placing a clustered column store index on it. Now you will say clustered column store index is required for indexing all the columns of a table. Yes, a clustered column store index is a special kind of an index that we place in a warehouse, and the most beautiful property of this index is it indexes all the columns of the table. Correct? It indexes all the columns of the table. So that means I can use any column of that table in a filter or in a joining condition. It will perform beautifully. We are saying it's not for a query related needs. It is not for join related needs. Then why are you placing a clustered column store index? Because always remember, index only improves the performance of a select query. The index does not improve the performance of inserts, updates, and deletes. Statistics improve the performance of insert, updates, and deletes. Indexes only improve the performance of select operation. And an index can degrade the performance of write and updates because it is a overhead, observer overhead. So an index can degrade the performance of inserts and updates. And you said it is for loading, that is insertions, not for selections. So why are you placing then a clustered column store index? The reason is cluster column store index also offers another beautiful property, which is called as column store compressions and column store archival compressions. So if your RR table is too large, RR table, round robin table is too large, which means it is in the realms of petabytes, okay, or several gigabytes, then it's good to place a CCI on that table, because that's going to give us compression, column store archival compression, CCI, column store archival compression, column store archival compression, and column store compression. So I am writing these as acronyms, so you may remember. Column store archival compression, column store compression. Yes. So what is round robin table? A round robin table tells the control node that that table is purely for loading needs. If I were to load the data from an external source, a lake, an external SQL server, whatever, if the data comes from external source, you load it in an RR to get the best performance. Some of the properties that you have to remember of RR is it's not a query table. You don't do reporting, dashboarding, ad hoc, or anything on it. It's not the part of dimensional modeling. It is just for importing the data. It has best loading performance. Because it is not for query, there is no need for an index, so it must use heap. But in some cases, you will find people developing a CCI on it, signifying that the RR table is large, so they are aiming towards compression models, column store compressions and column store archival compressions. Yes, round robin table, RR. Then what is replicated table? What is first of all replicated broadcasted model of distribution? Let us say table T1 is replicated distribution, uses replicated or broadcasted distribution. What does it tell the control node? It says fill the buckets in any way, take the rows and fill these buckets. There is no mechanism of filling them. So let us say you have a table T1. It has, let's say, 100K records in it. And the property that table T1 is using the distribution property of replicated. What does it tell the control node? It tells the control node you want to broadcast it. Broadcasting means what? You want to send all these 100K records to each and every guy. Broadcast means broadcast the entire table to each and every individual. Don't give them just buckets, part of the buckets. Earlier, what used to happen? Buckets used to get distributed, right? If 60 buckets are there, engines are 4, each one of them will get 15. So they get the part of a table, correct? A quarter of a table they get. Okay. You are saying, no, I want to broadcast the table. Broadcasting means I want to give the entire table to each guy. So they don't talk to each other. They have the full table. They have a photocopy of a table with them. Right? I am saying I want to broadcast. I want to send a photocopy of my table to each one of them. So that they don't talk to each other. They don't have any excuse. Hey, I didn't have the data. Right? No excuse. You have the full photocopy of the data with you. Okay, I want to broadcast. So it gonna be taking these rows, randomly it gonna fill it. Right? There's no strategy adopted. Gonna fill the rows here. Take some rows, some here, some here, some, and fill these rows. Right? After filling these, all the 60 buckets are given to each one of them, each engine. Broadcasting. You are broadcasting, correct? So what is broadcast strategy? Replicate strategy. You are saying, I want to replicate the table, the photocopy of the table. That is all the 60 buckets that I have, in which my table is now loaded. That table has to be given to each of the guy. Each and every individual must get it. How many I have here in my team, all of them must get the photocopy of that table. Replicate it. Why are you doing it? So that they don't talk to each other. That's the aim. They have the full copy of the table with them. There's no need to talk with each other. Simply do your work, complete the work, go home. That's it. Right? Don't talk to each other. So here, replicate it, broadcast it. What is that? But the buckets/node is not followed here. Yeah, distribution. All the buckets are sent. You are saying, no, replicate it. You're explicitly mentioning that that table should be replicated. That happens when you don't have replicated. If you have a replicated, you are saying it to replicate the entire table. So internally, it's gonna send the buckets containing your data to each one of them. Right? This is not punched on the stone, right? This can change. Yes. Right. So now the question is, table T1 is using the distribution property of replicated. We're going to come to the demonstration, then it's going to become super clear. Right now, I think we are imagining a lot of things, but I'm trying to explain the concept. T1 replicated 100K. Now the question that arises is, why would you use replicated? Simple. I want to send photocopy to each one so that they don't talk to each other. But then there is a restriction. What if your table is too large? Yes, so the recommendation from Microsoft is that the size of the table, total size of the table, should be less than 2 GB. So if you have a table whose size is less than 2 GB, you could very well keep it as a replicated distribution property on that table. Okay. All right. So what is it used for? It's a query table. It will become the part of your dimensional model. So what will you store in it? Your small dimensions. Small dimensions, size of the dimensions less than 2 gigs. Okay. So if the size of your dimensions are less than 2 gigs, you go with replicated. Then what? Now things follow. If it is a query table, you place index on it. What kind of an index? Obviously the CCI, clustered column store index. Can we also physically shard this table? That's possible. Yes, you can do partitioning. Right? You can do partitioning, range right and range left both. Right? So both partitioning strategies are allowed to you. Range right and range left, both of them are supported. You go ahead with both of them. Both are supported. So indexes can be placed, CCI, partitioning can be done, range right, range left, sharding, that means. So this is the thing, replicated tables. The last and the final one is the hash distribution table. Hash. Now, what do you use hash for? Hash. What do we mean by hash? Hash means keep rows together. Hash is a one-way function. We use hashes in modern cryptology. A hash is a one-way function. Can you please describe the RR table once more? What did you didn't understand in the RR? The question should be that. Because if I repeat it, let me repeat that, which is exactly what you did not get. RR is an external loading. You create a table RR and you load the data from external sources in the RR. Rows will be distributed in an RR fashion. So from the external table, you bring the data here. Let's say the external table has 30,000 rows in it. They will be filled in this fashion, round robin fashion. It's not a query table. It is for loading, known index required, a heap. CCI can be placed if your RR is too large, column store archival and column store compression. Right? Round robin, it will distribute the rows in a round robin fashion and then send the slots as per this strategy. Replicated, you are saying I want to broadcast the entire table. So it's gonna fill the buckets and send all the buckets to each one of them. All the buckets. Replicated, broadcasted, your full table is broadcasted to each and every one. Right? The last and the final strategy is a hashing strategy. A hash is a one-way function that you typically use in modern cryptology. It is easier to compute in one direction, but very hard to reverse. It's not possible to reverse the hash. So why are you doing hashing here? Take an example. You are saying T1 join the table T2, and you are saying T1 dot customer ID equals T2 dot customer ID. So then the question that arises is, wouldn't it be good to keep all the rows of table T1 and all the rows of table T2 where the customer ID is same in a single bucket? Keep them together. Let like people live together, right? So what does it mean? Take an example. I'm taking a very simplistic example to explain. So let's say this is the table T1, and let us say this is the table T2, right? So you have two tables over here with you, table T1 and table T2. They have a column, customer ID, correct? So cust ID, and here you have another column here as well, customer ID in the table T2. That's what you're doing, basic SQL. Let's say customer ID values are 101, 102, 103, 104, 101 again. I'm not seeing the customer ID is a primary key. 102, 103, 107, like this. Values are there in customer ID. Here you have 102, 103, 101, 107, 101, 102, 103, 104, like this. You are saying join the table T1 and the table T2 wherever the customer ID is same. So join all those rows where the customer ID is same. So what is the hash partitioning, hash distribution strategy? In the hashing, you have to tell it which column to hash. So customer ID is what we will tell it to hash on. So it's gonna compute the hashes of these columns. So hash of 101, let's say some number, right? It will compute a very long hash. Let's say the hash is A. 102 a different value, hash is B. 103 a different value, hash is C. 104 a different value, hash will be D. 101 hash will be same, A. 102 the hash will be same, B. 103 the hash will be same, C. And this is 107, so its hash will be E, a new hash. Here 102 the hash will be B. 103 the hash will be C. 101 hash will be A. 107 the hash will be E. 101 the hash will be A, 102 the hash will be B, hash will be C, and here the hash will be D. So what it's gonna do? It will take all the rows which have same hash. So A, 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 A. They have the same hash, correct? So the hashes are same for all these tables, all these rows, A, 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 A. Take all the rows and plug them into one of the bucket. Send all the 101s here. 101, 101, 101, 101 of table T1 as well as table T2. Okay, so these two rows are from table T1 and these two rows are from table T2. They are in the same bucket, like people live together here in this bucket because their hash was same. So two rows that you had in table T1 having the same hash, and the two rows that you had in the table T2 because their hash was same, both of them agreed that let's live together. So they went to this house and they're now living together. Now next, like people, right? So what's happening here? So you have B and B2 here, right? B, and then another B here, another B here, 4 B's. So 2 B's from here, 2 B's from here. They will live together, right? They're gonna live together. So they can go to 2 and they can even go to 1. They don't have any problem with ones, right? They are not in fight with one. What they want is to live together, right? 102, 102, 102, 102, all those 4 people, they want to live together. They are not in fight with this. So they can go here or here, depends on internal control node. Okay, so let's say 102, 102, 102, 102 of table T1 of the table T2 are here because the hash was same. They could have very well been put here. Sometimes people ask the question, can they go here? Yes, they are not in fight with 101s, right? The only point is they have to live together, right? They have to live together. That's what they say, right? So that's the thing, okay? And so on and so forth. So this all will be filled in this way. And then these buckets will be given as per this strategy to these guys to process. Now, what would be the advantage of this? Think about it. You are asking a join, right? So all the rows are in a single bucket. Let's say this guy is joining 102s. All the 102s are here. It will never ask, hey, I want some rows of 102 that you have. No. It has all the rows of 102 with him because all the rows are in a single bucket. And we send this bucket to this guy. This guy joins and send back the result because all the 102s were there in that box. Hash strategy. Hashing is used for joins, group by, clauses. So hashing is also used for query related needs. We use it for large dimensions and facts in your dimensional model. So you use it for large dimensions and facts. Okay. Large dims and facts, you use it for that, large dims and facts. It's a query table, so obviously a CCI. And obviously partitioning can be done. You can do the sharding of it. Partitioning can be done. It's a CCI. CCI can be placed on it, clustered column store index. Partitioning can be done. And then typical use cases are joins, where you can use it in where clause as well, and your group by clauses. The columns that you place in those wheres and group bys, better to have a hash on that column. So these are the three strategies that you typically use in order to fill these buckets that help us minimize inter-compute node communication. And these distributions are super important to be understood properly.
So guys, if you liked our video, then do give us a thumbs up. But if you really want to learn more about the particular topic we discussed, then we have something really special for you. We have our free class on Microsoft Azure Data Engineer certification, that is DP-203, along with some question and answers, where we'll be discussing about why is everyone working on data, importance of some Azure services you should learn, and many more things. So for that, all you have to do is just log on to K21Academy.com/Azure DE02, and after that you'll be seeing a screen like this. Just click on book your free seat now. Select your event date whenever you're available. Reserve your spot by adding your name, your email address, and your phone number, and you'll be getting all the updates via mail. You'll be seeing this kind of window on extreme right, so you can save this link, add to your calendars, and I'll see you in the free class. Till then, keep hustling and take care.